Welcome to CSC 201, Lesson 2.3, Valid and Invalid Arguments. An argument is a sequence of statements. All statements in an argument, except for the final one, are called premises, or sometimes assumptions, or sometimes hypotheses. The final statement is called the conclusion. To say that an argument is valid means that if the premises are all true, then the conclusion must also be true. To test an argument for validity, we use a truth table. First, we identify the premises and the conclusion of the argument. We construct a truth table that shows the truth values of all the premises and the conclusion. A row of the truth table in which all the premises are true is called a critical row, because that's part of the definition of a valid argument, right? If all the premises are true. So we identify rows where all the premises are true. And for an argument to be valid, the conclusion must also be true in every critical row. So let's practice one. Here is an argument, and we are going to determine whether it is valid or invalid by looking at this truth table. So P implies Q or not R. So remember, the implication comes last. The order of operations here says you would do the not R, then the or, then the implication. Okay, so P implies Q or not R. So that's one of my premises. I have to build up to it with the order of operations, but my premises are P implies Q or not R. Q implies P and R. Q implies P and R. So there's my two columns of premises. And then my conclusion is after the therefore P implies R. So my conclusion, whenever my premises are both true, my conclusion has to be true in order for this argument to be valid. So let's go ahead and work our way through setting up this truth table. So I have three statements, P, Q, and R. So I could have 8 different true-false combinations. Okay, so those are all my P, Q, R true-false combinations. Now I'm going to fill in not R. So I'm working on building the first premise. So I do the not first, then I do the or, and then I do the implication. Okay, so not R would be false, true, false, true, false, true, false, true. Q or not R. So I'm looking at this column, Q, and this column, not R. It's an or statement, so I need at least one true to get true. So true, false gives me true. Then true, true, true. False, false, that's false. Then true, 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 false, true. P and R. This is part of my second premise. I'm going to build them. I wanted the premises to be next to each other in the table, so I'm just going to build this part of the second premise first. P and R, so I'm looking at the P column and the R column. It's an and statement, so I need 2 trues to get a true. So I've got true, false, true, false, 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 false. And then now I can use the columns that I have to build my 2 premises, this whole statement and this whole statement. So P implies Q or not R. So I'm looking at the P column and the Q or not R column. So I'm going to be looking here and here. I'm looking for an implication, and an implication is false only when the if part is true and the then part is false. So I'm looking for true falses, and that will give me a false. So I have true, 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 false. That gives me a false. Then I have true, true, false, true, false, true, false, 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 true. So I only have one false in this whole column. The rest are true. Okay, and then my next premise, Q implies P and R. So now I am looking at the Q column and the P and R column. And I'm using an implication, which means, again, I am looking for true, false. I'm looking for places where Q is true, but P and R is false. That's the only way an if-then statement can be false. True, false. Okay, so Q, we have true, 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 false. Okay, false. Then false, true, false, false, true, false. There's another false. True, false. There's another false. False, true, false, true. So I've got 3 falses here. The rest are true. And then I'm going to calculate the conclusion. P implies R. Okay, so because we think that if these 2 things are true, then this last thing has to also be true. So I'm going to analyze the truth of P implies R. So I'm looking at P and R. And I'm going to look for true falses. P true, Q false, and that would give me a false for an implication. So I have true, 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 false. So that gives me a false. True, false. That gives me a false. False, true, false, 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 true, false, false. Okay, so the rest of them are true. Now I just want to identify critical rows. Rows in which all the premises are true. So I'm just going to highlight them in yellow. Rows where the premises are true. So that would be like this one. I have true and true. And then this one, I have true and true for my 2 premises. And then this row, my 2 premises are both true. And this one, my 2 premises are both true. Okay, for the argument to be valid, it has to be the case that if the premises are true, then the conclusion is true, but I've got this rogue column right here that makes the argument invalid. There is a case where both premises can be true, but the conclusion is false. Invalid argument. So we saw that the argument that we just analyzed with the truth table was not valid, but 2 examples of valid arguments are modus ponens and modus tollens. So the modus ponens argument says that if P, then Q. P, therefore Q. And modus tollens, which is very similar, but it uses the contrapositive, says if P, then Q, not Q, therefore not P. So that was a bit of an abstract introduction to those 2 arguments, modus ponens and modus tollens. Let's use those 2 arguments to complete each valid argument. If there are more pigeons than there are pigeonholes, then at least 2 pigeons roost in the same hole. There are more pigeons than there are pigeonholes. Therefore, at least 2 pigeons roost in the same hole. Okay, and then modus tollens says if 870,232 is divisible by 6, then it is divisible by 3. 870,232 is not divisible by 3. Therefore, 870,232 is not divisible by 6. We have several other rules of rules of inference, which is just a fancy word for valid arguments. Okay, so these are valid argument forms. The first one is a generalization rule. P, therefore P or Q. Or equivalently Q, therefore P or Q. For example, suppose you're given the job of counting the upperclassmen at your school. You ask what class Anton is in, and you are told he is a junior. You reason as follows. Anton is a junior. Therefore, more generally, Anton is a junior or Anton is a senior. Knowing that upperclassmen means junior or senior, you add Anton to your list. You obviously would not think all of those sentences in that really rigorous way, but that is what you're doing. That is how you're deciding to add Anton to your list. Then we have another set of valid argument rules called specialization rules. So they have the form P and Q, therefore P. So if you know P and Q are true, therefore P is true. Or P and Q are true, therefore Q is true. For example, suppose you're looking for a person who knows graph algorithms to work with you on a project. You discover that Anna knows both numerical analysis and graph algorithms. You reason as follows. Anna knows numerical analysis and Anna knows graph algorithms. Therefore, in particular, Anna knows graph algorithms. Accordingly, you invite her to work with you on the project. Elimination rules. So this is has an extra step, so I wrote the steps vertically here. So P or Q, if you know it is true that P or Q is true. Not Q, therefore P. Or P or Q, not P, therefore Q. For example, suppose you know that for a particular number, x minus 3 equals 0 or x plus 2 equals 0. If we also know that x is not negative, then x does not equal negative 2. So x plus 2 cannot be 0, therefore x minus 3 equals 0. This is where you eliminate one of two possibilities. So the or statement at the beginning gives you two possibilities. Then you eliminate one, therefore the third one remains. The transitivity rule is a very common one. It says that if P implies Q and Q implies R, then P implies R. For example, if n is divisible by 18, then n is divisible by 9. If n is divisible by 9, then the sum of the digits of n is divisible by 9. Therefore, if n is divisible by 18, then the sum of its digits is divisible by 9. Then we have proof by cases. So this is also a longer argument, so I put it vertically. So P or Q, we know P or Q. P implies R and Q implies R, therefore R. So if you know either P or Q is true, either one of them will imply R, so R must be true. For example, suppose that x is a non-zero number. It must be that x is positive or x is negative. Those are the only two options. That's my P or Q. X is positive or x is negative, my two cases. If x is positive, then x squared is 0. If x is negative, then x squared is 0. So my R is x squared is 0. Whether positive or negative, x squared is 0. Therefore, x squared is greater than 0. Sorry, I meant to say greater than 0. Therefore, x squared is greater than 0. Okay, so let's do an example where we're going to use several of these argument forms to try to solve a little mystery. You're about to leave for class in the morning and discover that you don't have your glasses. You know all of the following statements are true. So you have 5 premises. These are all true statements. We know that they are true. We're going to try to use them to create a valid argument that tells us where the glasses are. Okay, if I was reading my class notes in the kitchen, then my glasses are on the kitchen table. If my glasses are on the kitchen table, then I saw them at breakfast. I did not see my glasses at breakfast. Okay, so I can immediately do a little bit of backwards work here using the contrapositive. Okay, so A says that if I was reading my class notes in the kitchen, so let's say reading in the kitchen will be RK, then my glasses are on the kitchen table. Glasses in the kitchen, okay? And then B says that if my glasses are on the kitchen table, then I saw them at breakfast. Saw at breakfast, okay? And C says I did not see my glasses at breakfast, so not SB. All right, so remember that a conditional statement is logically equivalent to its contrapositive. So not seeing your glasses at breakfast implies that your glasses are not in the kitchen. Your glasses are not on the kitchen table, right? And same thing up here. We're going to convert this to its contrapositive form. If your glasses are not on the kitchen table, then you were not reading in the kitchen. Okay, so I have a few more statements that I know are true. I created two more statements, this one and this one, that I know are true. Okay, because I know this is true. So this being true means this is true, means this is true. Okay, now D says that I was reading my class notes in the living room. So let's say reading in the living room. Or I was reading my class notes in the kitchen. Reading in the kitchen. And then E is if I was reading my class notes in the living room. So reading in the living room implies my glasses are on the coffee table. Glasses, coffee table. Okay. So let's see what we can do here. So my argument, I'm going to start with the premise that I did not see my glasses at breakfast. Not SB. Since not SB implies not glasses on the kitchen table, my glasses are not on the kitchen table. Okay. And since my glasses not on the kitchen table means I was not reading in the kitchen, I was not reading in the kitchen. And then D here says that I was either reading in the living room or the kitchen, but I was not reading in the kitchen, so I must have been reading in the living room. Reading, living room. And if I was reading in the living room, then my glasses are on the coffee table. Therefore, glasses, coffee table. A fallacy is an error in reasoning that results in an invalid argument. So some common fallacies are the converse error, where your premise is P implies Q, Q, therefore P. Okay, so here's an example that should clarify why this is not valid. So if Zeke is a cheater, then Zeke sits in the back row. Zeke sits in the back row, therefore Zeke is a cheater. It seems intuitive that sitting in the back row does not make you a cheater, right? Being a cheater implies sitting in the back row, but the other direction is not true. Sitting in the back row does not imply cheater. And then the inverse error, where you assume P implies Q. You know P is not true, therefore Q is not true. Okay, this is not true because when you include these nots, you have to use the contrapositive. Okay, so another example that should make this clear. If these two vertices are adjacent, then they do not have the same color. These two vertices are not adjacent, therefore these two vertices have the same color. So the premise says that if you have two adjacent vertices, they do not have the same color. So I've drawn a square, and each vertex has a color, right? If two vertices are adjacent, then they do not have the same color. That's true. If you pick any two vertices that are adjacent to each other, they do not have the same color. But if you pick two non-adjacent vertices, they don't have the same color either. You can't conclude that they have the same color. So this is an invalid argument. Okay, so there is sometimes confusion between a valid argument and a sound argument. So those are two different things. So we're going to look at these two arguments, and we're going to decide whether or not they're valid, which we know enough to be able to do, and then do we agree with the conclusion? Okay. So if Canada is north of the United States, then temperatures in Canada never rise above freezing. Canada is north of the United States, therefore temperatures in Canada never rise above freezing. Is this valid? Yes, this is the modus ponens rule. We have if P, Canada is north of the United States, then Q, temperatures in Canada never rise above freezing. Okay. P, therefore Q. Okay. Yes, valid. Do we agree with the conclusion that temperatures in Canada never rise above freezing? No. We'll just say like disagree with conclusion. So the problem here was with our premise, right? This if-then statement, what makes the argument valid is that if you accept the premises as true, then the conclusion must logically follow. So if we accepted these first two statements as true, it must be that this statement is true. But this first statement, if P then Q, is not true, right? It's not true that if Canada is north of the United States, then temperatures in Canada never rise above freezing. So we have a false, because false premise. We have a false premise. Okay, that makes the argument unsound. It's valid reasoning, but an unsound argument because it has a false premise. Okay, here's another example. If New York is a big city, then New York has tall buildings. New York has tall buildings, therefore New York is a big city. Is the argument valid? And the answer is no. Okay, the reasoning is that we have if P, then Q. Okay, P is New York is a big city, Q is New York has tall buildings. Q, therefore P, is not valid. Okay, this is the converse error. Okay. However, the conclusion is correct. New York is a big city. So that is also an unsound argument, right? We came to a correct conclusion, but it is not a valid argument. So those two arguments are called unsound. An argument is sound if and only if it is valid and all of its premises are true. Okay, lastly, we're going to discuss proof by contradiction. It's a very common method of proof. It says that if you can show that the supposition that the statement P is false leads logically to a contradiction, then you can conclude that P is true. So the argument form looks like not P implies C. It says if P is not true, then we get a contradiction. Therefore, P is true. So let's show that this argument is true that this argument is valid by creating a truth table. So I have it set up already. P and C are my only statements. So P can be true or false, but C is always false. A contradiction is always a false statement. Not P would be false and true, and that should be enough to be able to fill in my premise, not P implies C. So remember, the argument we're testing here is not P implies C, therefore P. Okay. So that says that if P is not true, then you get a contradiction, therefore P must be true. Okay, so not P implies C. Remember, the only way to get a false in an implication is if the if part is true and the then part is false. So that happens here, true, false. So that's going to be false. And the other one is true. And then my conclusion is P. I'm just going to restate it here. And I need to look at the critical rows where the premise is true, so only this one. And it turns out that when the premise is true, the conclusion is true. Whenever the premise is true, the conclusion is true. So this is a valid form of argument. Okay? If you assume that something is not true, argue with perfect logic, and you reach a contradiction, you know that your assumption that P was not true must be false. So here's a little fun example. A famous logician describes an island containing two types of people, knights who always tell the truth and knaves who always lie. You visit the island and are approached by two natives who speak to you as follows. A says, B is a knight. B says, A and I are of opposite type. What are A and B? Okay, so we're going to use a proof by contradiction. So we're going to start with a supposition. Okay, so we're going to suppose A is a knight. All right. Therefore, what A says is true. Okay, because A is a knight, what A says is true. That's the definition of a knight. Okay. A says that B is a knight. B is a knight because A says so, and A tells the truth. Okay. Which means A and B are both knights. Okay. So we can now argue, we now have enough to say A and B are both knights. However, B says A and I are opposites. Right? That contradicts the conclusion we just came to, that A and B are both knights. Right? And if B is a knight, then what he says is true. B says A and I are opposites, which is true because B is a knight. We have reached a contradiction. So you can highlight it or underline it. A and B are both knights, and A and B are opposites. Okay, we've argued until we reached two opposing conclusions. So it has to be, the only thing that could have happened is this very first sentence that we assumed at the beginning, that A is a knight, was false. So we have a contradiction. Therefore, A is a knave. It must be that A is a knave. Okay. Which means B is a knave because A lies. Okay. Thus, B is a knave because A says B is a knight. and A is a knave, which means A lies. So A and B are both knaves. And then we have this little summary of some of the most important rules of inference that we've talked about today. We went through all of them in the lesson, and this is just a little table that summarizes them.